All right, we're good to go. David, you're the man. David, thank you, thank you. All right. Death by electric circuits. All right, it's that time. All right. These are all up on Blackboard. The way I like to do these kind of classes, most of my classes, is I do a lot of work at the board. Problems. We solve problems, okay? So I'll kind of touch a little bit on the theory, but I like to do problems. Because really, the only way you get any better at this is to do what? Problems. You think Michael Jordan became a great foul shooter by not practicing his foul shots? No. He practiced his foul.
That would be one too, huh?
That's right. If you look at it. I looked at the Temple team this year.
Yeah.
What did they shoot in the second half of the game against Miami?
Yeah.
What was their shooting percentage? 0 for 15.
0 for 15?
0 for 15. It was bad. It was that bad. And they only lost by 3, which is hard to believe. But okay. Yeah. All right. So this is going to be integrals and electric circuits. You've done some integrals with Dr. Ryan? Or tried to do some integrals? Looked at the book. It was one of those kind of sessions. All right. Well, we won't be looking at the book. I mean, I'll be opening the book to find a problem in the book, but we won't be reading from the book. Okay? All right. So how's everything in general? Good? Hard. That's what engineering is about. I mean, it's got to be a labor of love. Really, you got to look at it that way. I mean, you got to get up in the morning and enjoy what you're doing. If this isn't it, go find what it is, because it's out there somewhere, huh?
I have 6 classes next year, and then junior year I have 7 classes.
That's you doing 18 credits?
Huh?
How many credits?
17?
Yeah, be careful. Especially, I mean, I'll give you a little bit of my history, because I'm from here. I think I told you, right? I mean, I was in this building in '78. Up here doesn't always. I have a little AD stuff going on and all that kind of stuff. It took me 5 years because I didn't want to do I couldn't handle 17 credits. I just physically couldn't handle it. I mean, I literally said, Dad. Well, Dad didn't worry about it because he wasn't paying anything. I mean, he would throw me on the train every morning. That was nice of him, but, you know, good. But it literally took me 5 years because I had, at times, I was taking 13 credits, 15 credits. But my goal was to get the degree done with a good GPA so I could get into graduate school. That was my goal. I was fortunate enough. I mean, I paid an extra year in tuition. Back then, it was $700 and something. Oh, wow. Yeah, I mean, back 700 something bucks, yeah. I know, yeah. It's ancient times, it seems like. But I know. One of the things, if your goal is to get this degree, you got to plan it out and say, you know, this is how I'm going to do it. I'm in my microprocessors class today. Half the students are working 20, 30 hours a week. They're just not making it. You've got to you got to get your life set up so you can succeed. That's the idea.
I'm just trying to follow the paper that they gave us. So, yeah.
I understand the fly-in for methodology and all that stuff. There's a lot to be said for that, but some people it just doesn't happen. And I know I couldn't fly in for it. Maybe now, but you know. Yeah, that was right. We like your money. We really like your money. But no, really, I just want to. If this is it, you've really got to look at it as, you know, the math. The reason that the dean's introducing this is that we lose most of the students. I mean, most of you, not we, but drop and move on to something else because of the math. I mean, it's when you get to the Calc 1, Calc 2, Calc 3. I had real issues with it, but I had to sit. I lived in the Math Science Resource Center. Literally lived in there, did problem, because I had somebody like Peter right there to help me immediately. You know what I mean? So it was, you know, I got to know all those guys that worked there and gals that worked there by their first name, and it was just, that's what we got to do. All right. So I'm just trying to give you, you know, this is where I come from a little bit, all right? So all right, so we're going to get into, these are what are called induction coils and capacitors, and the reason we get into integrals is because all these guys, they discharge and charge voltages and currents time varying. So if you go back to when you had systems of equations and you did circuits, it was all DC, right? I mean, the currents and the voltages, you just found, oh, there's 3 volts at this node, 2 amps through this element, and they were constant because all the sources were DC sources. Here we're going to have these generate AC, and actually, if we all take a look, you know what? We can all probably see one. Yeah, on that telephone pole over there, you'll see 2 big cylinders that are on there. Anybody know what they are? Transformers. Why do we have transformers?
Because when the power comes out the plant, it's too strong, so we need it to transform the current down so it can go through our houses.
Well, no, the idea is an Edison and a guy by the name of Tesla. Anybody hear of Tesla?
Eric Tesla?
No, Nikolai Tesla. Here's what was happening. Edison's in the middle of New York. He wants to generate electricity and transmit it because he invented the light bulb. I want to make money. All right? So he builds these DC generators, all right, that just generate DC current. Now, you know, as the line gets longer, the resistance goes up. What happens to the current? Start going down. So the people at the end, miles away, they go to hit the light switch and there's no light. Okay, so Tesla, who worked for Edison, says, Mr. Edison, you got this all wrong. If we use a sinusoidal signal, all right, that's time varying. So here I have, now the whole reason that this works is due to that transformer. The transformers typically, you can have just a single core with a winding on it. And this has a number of turns N1. And then on the secondary side, there's another number of turns N2. There's a V1 here and a V2 here. Okay? Now, this is the power plant. All right? The idea behind the transformer, this is how it works. If I send current through a wire, what happens around that wire? You generate a magnetic field. Okay? And that's the key. Because now I send the current through here. Right? Again, I have some generator sitting here. All right? I send the current through here, that generates a magnetic field, right? Through that wire. That might, and then that generates a magnetic field, I'll call it just phi of t in here. When I have a coil of wire in a magnetic field that is varying, what happens in that coil of wire? Okay. Forget the left side. On the right side, I have, and I'm going to have some load over here. This could be, you know, your light bulb or whatever. I have a varying, if I have a time varying current here, I of t is A sine of omega t. Okay? I have a time varying current here. That's going to generate a time varying magnetic field in this magnetic core. You agree with that? Does that make sense? Now, if I have a coil of wire, and let's say I have a magnet inside of it, north, south, and I connect these two ends to some kind of load, if I move that magnet up and down, anybody know what happens inside that coil of wire? Induces a current according to Lenz's law. If I have a closed wire, and I did this, I have some videos of this. And you could do it. You take a nice strong magnet, wrap a coil of wire around it, get that thing. Now, it won't do it if the magnet is stationary. It has to be a time-varying magnetic field to give me the time. So then, what that's going to do is going to induce a current over here, I2 of t. Okay? So, time-varying current generates a time-varying magnetic field, which generates a time-varying current. Now, you may say, yo, Doc, why don't I just hook this wire to that wire? The reason is the turns ratio N1 over N2. You don't have to write this down. I'm not going to quiz you on this, all right? So what you have here is V2, the ratio of V2 to V1 is equal to the ratio of the turns, N2 to N1. So now what happens here, if I make these turns much higher than these turns, V2 is going to get amplified, right? Because I just bring V1 over here. This number is going to be greater than 1. So now V2 goes up. All right? So Tesla says, wait a minute. If I sit here at a generating station and I now make N2 really big compared to N1, I'm going to generate a high voltage here at a low current. The power, you can't get more power out of this. The power on this side has to be the power on this side. He says, you know what? But if I can get those voltages to go way up and attach them to a transmission line, those voltages with very small currents can travel a long distance. And then what I do is I step the voltages. So these transmission lines are 50 kilovolt, 100 kilovolt transmission lines. Is that what's coming out of your wall? No, what's coming out of the wall? Usually 110 volts, 110, 120 volts. So what you do is you start at the power plant, you generate high voltages here and transmit them a long way. And then what do you do with the telephone pole? You step it back down. You use a step-up transformer to ramp it way up. Off it goes. You get to the little house down here, you collapse it back down. Okay. Now you're going to lose power in these lines, in the transmission lines, but you're not going to lose as much as you did with DC. That's why. Anybody ever hear of Westinghouse Corporation? Westinghouse, George Westinghouse. What did he do? He said, Mr. Tesla, you're coming with me. What happened to anybody know? What happened to Edison's DC? You don't see it out there, man. You know who? You ever hear of General Electric? It was Edison Electric before it became General Electric. He got the boot because he wasn't making the money. Mr. Westinghouse and Mr. Tesla went up to, I think it was close to Niagara Falls. They made a big hydro generation plant. Started transmitting it all over the place. And the interesting thing there is, again, how a hydroelectric plant works is you have, think of my feet as turbines that are in the water spinning. On my arms, I have big magnets. And what do I put on the walls all the way around? Shoo, shoo. I'm doing this. Shoo. So what's happening to the wires that are in the walls? You're inducing a current into them. And that's how you generate hydroelectric power. It is. That's the real deal. You got any hydro plant, you'll see them. They spin these turbines up thousands of RPMs. You have big stationary magnets on the end of these coils, the end of these arms that are out, and then you just, you spin them real fast, and you're you're generating high magnetic fields that are time varying. And that's how you do it. That's the transformer. Okay? Life wouldn't be the same without the transformer. All right. Get the idea? All right. Capacitors, okay? This is what we batteries got capacity, man. All right. Anybody have a flash camera? Flash camera. All right? Flash camera, all right? Do you have to wait for it to charge up? Yeah, the ones now probably don't, but the other ones 10 years ago, you have to sit there, you'd have your battery, you had the flash, and what you did was the battery didn't get directly connected to the flash because the battery can only produce power at a constant rate, and what you need is a big flash, instantaneous. Well, what we do now is we charge up two plates, one positive and one negative. So you sit there with your camera and you hold it and you'll see a light flicker, and all of a sudden when it gets to a constant value, the capacitor's fully charged. You press the button down, the capacitor then discharges through the bulb, and you get an instantaneous flash. So that's what these guys, capacitors have the ability to hold charge. And effectively what you have is a metal here, and then what we call a dielectric in between them. You can't conduct in here, all right? That you can't conduct. So what we're doing is we're going to store charges on one plate, store them on another, and then I can walk away and come back a year later, they're still going to be charged. Or I can throw a switch and then have them discharge. I've actually, up in my lab, I've melted two screwdrivers together by connecting them to capacitors. I think I have the video. I'll bring it up in a minute. So that's what we have. It's a passive element to store energy in an electric field. In an induction coil, you're storing energy in a magnetic field. Here we're going to store it in an electric field, all right? It's two parallel plates separated by an insulator. Okay? So that's what we have. Battery can deposit positive charges on here, negative charges on here. I now have an electric field between these two, but I don't want the charges from the one plate to jump to the other plate, because then the electric field will collapse. Because remember now, anybody remember Coulomb's law? You're looking at me funny. You have two charges. The force, it could be attractive or it could be repulsive, but it's K, Q1, Q2 divided by R squared, okay? So if I have a charge here and a charge here, there's a force, and the electric field is defined as the force per unit charge. So the electric field is set up between those two plates. If those two plates come into contact, the electric field collapses. So now what I want to do is keep those charges separated on these plates. All right? Keep that. There's got to be some distance between these guys. I could have used D down here or whatever, but D. All right? As D gets closer, the force goes way up and the electric field goes up. Okay? It's the same capacitor. You can think of it also as, anybody ever been out? All right. I have a cloud. Here I am down here. The cloud is typically negatively charged on the bottom. What happens to my hair? It starts to go up, right? And that's that force. That's that Coulomb force that's acting upon it. All right? All right. Enough with the commercial. I forgot. Never wear blue when you're working at a chalkboard. I forgot this morning when I was getting dressed. Now I'm going to be wearing chalk. All right? All right. Don't hesitate to ask any questions. Capacitors. So what you can do is you have these. Hold on. I'll get to you in a second. Now, you may say, all right, it's big plate, capacitors are going to be big. You can make them smaller by having these two plates and just rolling them together into a cylinder. I'll show you how to do that in a second. So that's what this guy is. You've got two electrodes, a medium anxiety here. That's what one looks like. If you have any old TVs at home, don't go poking around in the back of them with a screwdriver, because they still have the charge on them. You put anything between those two terminals, you can kill yourself. All right? It stores a lot of charge. So what they do is, that's how we, instead of having these big plates, you take the aluminum, metal foils, you have the dielectric, and then you roll them up, and it puts it into a nice can. Okay? So you can get a lot of area in a small, compact device. All right, and as I mentioned, that's how a flash camera works. What you have is flash camera. Down here, I have a flash capacitor that's sitting in here. Here's my flash bulb here. Battery sits down here. What you do is you charge up this capacitor. All right, so now you just sit there for a few minutes. The light's going to flicker, and once it gets steady, that thing is fully charged. Then what you do is, boom, you hit the switch. The battery comes out of the circuit. This capacitor gets connected into the flash side, and you get that brilliant flash coming out. So capacitors can store energy in an electric field, and then we can bring that energy back when we want to use it for something. Okay? So that's the flash capacitor. All right, so the idea is you can think of this as current deposits, negative charge on the other end, and you can think of it like a balloon or a membrane. You blow it up, and then I can use that energy to come back later. All right? That's what you can think of it as. You think of it as blowing up a balloon and then releasing it, and it can go flying around because now you've stored all this little energy in it. We also have capacitors are in your little microphones. All right? What you effectively do is I have inside the microphone, here's a battery. Okay? Here's one plate that's going to be positively charged. The other one is negatively charged. My damn dog just ate my mic. I couldn't believe him. I have a new dog, Cody. They eat anything. I left my earbuds and my radio sitting out. Chewed the damn thing up. I should have brought it in. He had him, because you could see the capacitors in there. What is happening here is you charge one plate positive, the other plate negative. And as I talk, my acoustical wave comes in and hits this thing. What's going to happen to this outer plate? It's going to start moving, right? Because and it's going to go like this. Now remember, we have the capacitance is going to be defined as epsilon, the area divided by the distance. The area of the plates divided by the distance. So now, as I start moving this diaphragm in and out, what happens to the capacitance? What happens to D? This distance is going to get longer and shorter, so the capacitance is going to start changing. What will happen is the current coming out of this device will start changing. It'll change according to the pattern of which I'm speaking. So I run this down through an amplifier to a speaker, and I can speak to the heavens. All right? So you're literally moving that diaphragm, and then you're going to get a current down here that's going to mimic that wave, which is pretty freaking cool. All right. So as it goes in, I will get an electron flow, and as it goes out, you'll get a different one. So I'll get a positive flow, a negative flow, depending upon what's happening with these plates. All right. All right. So Q is equal to CV. The charge on a capacitor is equal to the capacitance times the voltage across the plates, and we define capacitance to be, this is the permittivity of the material, of the dielectric, the cross-sectional area. The bigger the area, the bigger capacitance. The less distance also gives you a higher capacitance. Okay? Yeah, go ahead.
What does Q stand for?
Charge. I'm sorry. This stands for charge in coulombs. That is charge in coulombs. Okay? V is in volts. Okay? Do you guys, you know what current is, right? Okay, because if I take Q is equal to C times V. If now Q is time varying and V is time varying, I have dQ of T dt is equal to C dV of T dt. What's dQ dt equal to? Current. That's I of T. That'll be I of T. Does that make sense? So now, when we have this differential relationship, let's say I know what the voltage is across a capacitor and I want to find what the charge is. Okay? So now, well, if I have I of T, whoops, I'm going to have Q of T is equal to I of T dt, right? Is that okay? We're just looking at this part here. So now, if I integrate, oh no, this is dQ of T, yeah. So now I integrate, I'm integrating with respect to charge here, so this is going to be Q at T0 up to some time Q of T of dQ of T is equal to the integral from some time T0 to T of I of T dt. Is that okay with everybody? Solving for the integral there? On the left-hand side, you get Q of T minus Q of T0 is equal to the integral from T0 to T of I of T dt. Okay? All right, so therefore, effectively what we have is I can find the charge at any given time by knowing, I have to know the current I of T dt plus Q and T0. I can find if you tell me what the current is, I integrate the current to find the charge. Okay? That can tell me what's happening there. All right, and we have for the capacitor, epsilon is called the permittivity, A is the cross-sectional area, D is the distance. The units for this are what we call farads. And it can be in picofarads, nanofarads, microfarads, millifarads, whatever. Okay? All right, so we have the symbol for a capacitor, the voltage and the current across it. So there we just solved for, just as I showed you before, Q of t is the integral from t0 to t, I of t, plus the initial charge that's on that capacitor. All right? I have I is equal to the capacitance times dV dt. If I solve for dV, I end up with this expression. So therefore what we have is, these are the two expressions you're going to need for this chapter, okay, for at least the capacitor part of this chapter. Okay? So we have dV of t dt, C is equal to I of t. So now we solve this, we're going to have dV of t is equal to I of t divided by c times dt. Integrate both sides, v at t0 to v of t. Integrate this side from, it's not, now you're integrating this side with respect to voltage, that's why the limits are voltage. What am I integrating this side with respect to? Time. So this has limits of t0 and t. Okay? The left-hand side comes out to be v of t minus v of t0 is equal to 1 over c, the integral from t0 to t of I of t dt. And that's this expression here. Just bring the t0 over to the other side. All right, so these are the relationships as you have them in the book, okay? Integrating v of t, and I guess it's that guy there, all right? Actually, let me show you a quick video. Is it warm in here? Yeah. Wow, I'm glad I'm not alone then, all right. So I'm starting to get a little dew on the brow. A little dew on the brow, as they say. You never heard of that expression?
No.
Huh?
From the south.
A little bit. A little dew on the brow. We'll have fun, gang. You got to have fun. There we go. That's what I wanted to see. All right, I want to show you. Here's a little capacitor. We took a camera apart. Hold on, let me. It runs into another video in a second here. So we took a digital camera apart. So we just charged it up here, and then I wanted to show you that in the next one, in here. There's the. Why do you keep doing that to me? Well, now we're going to put a wire. I mean, a little. All right, little poof. All right, but that's the idea. Is that capacitor? We charged it up, and then we came back and put the wires across it and discharged it. You could see that thing. And it welded the leads together. So it's a pretty good bite you can get out of that thing. That's a good question. I have to go back and find the camera. I mean, but it helps. I mean, there was some. I tell you what, when you go back, like the blue ones I was showing you earlier, I got to find that video because I hooked a whole bunch of them in parallel. I had one wire connected to a screwdriver, another wire connected to a bolt. And I ever so gently, I had insulated gloves on, put them together. I mean, the sparks were flying, and it arc welded it. It literally welded it, yeah. So that's why on old TVs, don't go poking around in there with a screwdriver, because if there's capacitors in there and they're charged, you can get killed. I mean, they even say, on the back. All right. The other videos are an induction. Oh, here's a good one. This is my phone bug. I don't want a slideshow. I want to run this thing. Yeah. Don't you just love Windows 8? I really, I mean, I'd rather poke my eyeballs with a needle or something than play with this thing.
I think it's because they stepped it down to.
There's so many glitches.
What's that?
I'm used to
I
it.
heard they stepped it down to Windows 7. It has like the Windows 8 look, but it's actually like Windows 7. That's why I can't get
That's a photo. Or no.
Oh, that's the photo, yeah.
You said you were going to show us the screwdriver that you took.
I don't see it here. Oh. This is a phone bug that we made. I transmitted to a radio. Yeah, like 88.5 or something. It has a little amplifier in it with a little capacitance, and whatever voice goes down through the wire, I pick up that current, and then I send it through a little antenna, and I have to tune it with a capacitor, and I had my analog FM radio sitting over here, and it'll go for about 100 feet. So I could put that phone bug in there, and then I could sit 100 feet away with a radio and listen to you. You know, there's a little capacitor in there. Yeah.
A lot of trouble with that.
Yeah, actually, you can get in a lot of trouble. Yeah, just ask my daughter. Oh, come on now. No, just kidding. Just kidding. I'm not like that. No. All right, so these are the relationships for voltage and current in a capacitor, okay? All right, so let's start doing some problems. All right, so now what we have is we're going to have a current of 6 sine 4t flows through that 2 farad capacitor, okay? So I have this current coming up through here is 6 sine of 4t. It's time varying, and a capacitor is a 2 farad. What we want to do is find the voltage across the capacitor, given the capacitor has an initial voltage on it of 1 volt.